Supervised machine learning is a branch of machine learning where we are interested in taking our data and classifying that data to either two classes or a multitude of different classes. And to begin, let's focus on the binary case where we have two classes and we're interested in drawing a boundary decision on that data set. Let's get specific. On the screen, you see blue dots and red dots, and there's areas where the blue dots and red dots overlap. The goal of this video is to try to figure out an algorithm to draw boundaries around the red and the blue dots so that they're segregated. To our surprise, we can actually start doing this rather intuitively. So think about how these dots are related to each other. Are they close? Are they far? Are there ways that we can figure out if there's more blue dots in a region versus a different region? And this requires us to develop a notion of distance. At least for the purposes of this video, we can use a more intuitive understanding of distance, meaning that we're going to use the Euclidean distance to measure closeness, or how far one point is from another point. It should be noted that there is no restriction on what metric can be used. The only requirement to use k-nearest neighbors is to ensure that the metric being used belongs to a metric space. Cosine similarity, for example, would not be a good choice because it's not a metric. This can lead to numerical instabilities, for instance, and can break down the algorithm. So it's important that you pick metrics that belong to metric spaces. Keeping this notion of distance in the back of your head, let me show you some images of dots, and then you tell me where this yellow dot belongs, in the blue group or in the red group. In this first image, it feels like the yellow dot belongs to the blue group because, well, it's closest to the blue dots. And in this next image, you see that the yellow dot is closest to the red dot, so it feels like it's part of the red group. I felt as though those previous examples were kind of straightforward, but what about this one? So again, yellow dot, red and blue dots, where does that yellow dot belong? And it's not entirely clear because let's say that we're only looking at the three nearest neighbors to that yellow dot. Now it belongs to the red group, but if you look at the next 5 neighbors, now it belongs to the blue group. And so how do we go about determining where that dot belongs? This is when the notion of a ground truth comes in. And so what we do is we tune the algorithm to match well with the ground truth. And so we have 2 classes. And what we do is we then train the algorithm to be the most accurate with 3 neighbors or 5 neighbors based on the ground truth that's given to us. Just to hit the point home, I coded this up in Python and I plotted the boundary decision for k-nearest neighbors for the scenario I showed at the start of the video. And you can see how the boundary decisions develop as you add more and more neighbors. The case to ignore is k equals 1 because that will always give an accuracy of about 100%. But I always find it interesting to notice how this algorithm finds nonlinear boundaries between points, where they might be difficult for other methods to pick up on those nonlinear boundary choices. Here's the same thing but sped up. This does not mean that taking n to the largest number gives you the best result, but it shows some type of numerical stability when dealing with data that comes from normal distributions. That's all I have. Thanks for watching.